Earlier in the chapter, I had referred to something known as the roadmap, and this is the roadmap. If you go to my home page and go under the probability text section, you will see something that says Chapter 7 Roadmap. It is a PDF file, and if you print this out, I would like you to fill in all of these blanks as we do the examples. Because the examples take a while in this chapter, we're only going to do one of each type of example. After you see that example, it's worthwhile going to the textbook and reading 2 or 3 more examples of the same variety to get the hang of it, because it's very difficult to get the hang of these techniques from just looking at one of these. So in terms of techniques, the first technique is the cumulative distribution function technique. That's going to be covered in section 7.1. And then in section 7.2, the transformation technique will be introduced. And then finally in section 7.3, the moment generating function technique will be introduced. Now in 7.1 and 7.2, we'll start with the univariate case, move up to the multivariate case, and in each case that's broken down into discrete and continuous. In 7.2 we start with the univariate case, move up to the multivariate case. And in 7.3 we go straight to the multivariate case, don't even need the univariate case in that particular situation. Now in terms of examples, this first case here, the example that's about to be done, x will be a geometric random variable with parameter p, and we will be interested in the distribution of y equals x squared. And that is example number 7.6 from the book. In the next case, we're going to let x be a uniform random variable between 3 and 5. And the transformation of interest will be y is equal to the square root of x. That is example 7.8 in the text. Then in the multivariate discrete case, we have 2 random variables. And for these 2 random variables, in the first case, we're going to let x1 be geometric p1. So I'm going to have to write kind of small here. And this is lowercase g, geometric with parameter p1. And in the second, we will have x2 be geometric with parameter p2. The interest here will be in the transformation y is equal to the minimum of the random variables x1 and x2. This particular example is example 7.10 from the textbook. At this point, we're going to let x1 be a uniform 0, 1 random variable, and let x2 also be a uniform 0, 1 random variable. When you look at that particular example, we'll be considering the random variable y, which is the product of x1 and x2. That particular example is 7.12 in the text. Now at this point we return to the discrete univariate case, and we actually rework this same example right here. That is x coming from a geometric random variable, geometric distribution with parameter p, and we rework this same example, which is of course y is equal to x squared, and that particular example is example 7.15 in the book. However, this time instead of working that example using the CDF technique, the transformation technique is used. Then in the continuous case, x will be an exponential random variable with parameter 1, and we will consider the distribution of y equals 4/3 pi x cubed, and that particular example is 7.18 in the textbook if you want to look that one up. Then when you go to the discrete case, there will be x1, which has the Poisson distribution with parameter lambda 1, and x2 also has a Poisson distribution, but this time with parameter lambda 2. And this time we're interested in y, which is the sum of x1 plus x2, and that's going to be example 7.22 in the textbook. Then for the continuous multivariate case with the transformation technique, the random variable x1 will have the uniform distribution between 0 and 1, and the random variable x2 will have also the uniform distribution between 0 and 1. And the interest in this particular example is to find the distribution of y, which is again the sum of x1 and x2. And that particular example is given as 7.25 in the text. So as you can see, just from the numbering of these examples, there's a lot of examples that are not covered here in the notes, and so you want to read the examples in between. Finally, in the discrete continuous case, we're going to let x sub I be Poisson with parameter lambda sub I, and that will be for I equals 1 to n. And in that particular case, we're interested in the distribution of the sum of n of these random variables. And that one right there will be example 7.29 in the textbook. Finally, the very last one in the moment generating function technique in the continuous case, in that case x sub I will have the exponential distribution, this time with parameter lambda, and the interest will be once again in y as the sum, because the moment generating function technique is particularly good with sums of those x sub i's, and that is example 7.30 in the book. So again, in this chapter we're not going to do all of the examples, nor have we in the past, but we're doing so few of them that it's worthwhile showing you where everything is headed from this particular roadmap.